Consider a circle of center O. If you allocate a sense of orientation to this circle where counterclockwise marks the positive sense and clockwise marks the negative sense, this turns the circle into an oriented circle where all angles turn into oriented angles. What this means is that if we open a 60-degree angle counterclockwise, it would measure positive 60 degrees, while if we open it clockwise, it would measure negative 60 degrees. But what is the unit circle? The unit circle is in fact an oriented circle of radius 1 unit. But what does that have to do with the trigonometric ratios? If we introduce an orthonormal system on the unit circle with its origin at the center of the circle, this yields the vertices of the circle on 1 and negative 1 on both axes. Considering a point P on the circle forming an angle of theta with the positive x-axis, the circle being a unit circle, we have OP equal to 1 unit. Now let's investigate the coordinates of P. Starting with its abscissa x of P, the orthogonal projection of P on the x-axis forms a right triangle where xp is adjacent to theta and OP is the hypotenuse. Adjacent over hypotenuse is cosine theta, which yields cosine theta equal to x of P over 1. Then cosine theta is equal to x of P. Then the abscissa of P is cosine theta. Now projecting P on the y-axis to find its ordinate y of P. Y of P is nothing other than the orthogonal distance between P and the x-axis. In the same triangle, y of P is opposite to theta and OP is the hypotenuse. Opposite over hypotenuse being sine theta, then sine theta is equal to y of P over 1, leading to sine theta equal to y of P, then the ordinate of P is sine theta. Using Pythagoras' theorem in the formed right triangle, we deduce that cosine squared plus sine squared is equal to 1 for all theta, a property called the Pythagorean identity. In conclusion, any point on the unit circle has cosine theta and sine theta as its coordinates. Consequently, the horizontal axis is the cosine axis, while the vertical axis is the sine axis. Now let's check out this animation. As P moves along the circle for all theta, cosine theta and sine theta are always bounded between a maximum and minimum of 1 and negative 1 on their respective axes. Consequently, cosine theta and sine theta are always between negative 1 and 1 for all theta. But what about tan theta? Tan theta being the tangent ratio of theta, let's draw the vertical tangent to the circle at the point 1, 0. Let's extend OP to intersect the tangent we considered. Naming all the points we need, let's name Q the projection of P on the x-axis, T the intersection of OP with the tangent, and A the vertex of the circle at the point 1, 0. We have triangle OPQ we previously worked with, and now we have triangle OAT that we formed by intersecting OT with the tangent. The two triangles being similar triangles, we then have from the first triangle OQ, which is equal to cosine theta, divided by OA from the second triangle measuring 1 unit, equal to PQ from the first triangle measuring sine theta, divided by AT from the second triangle. Rearranging the obtained proportion, we obtain AT equal to sine theta over cosine theta, which is tan theta. Then distance AT is in fact tan theta. Now the vertical tangent we considered is in fact the tan axis. Now before we end this video, I will leave you with a small investigation question. If cotan theta, being the reciprocal of tan theta, is cosine theta over sine theta, then where can we locate the cotan axis on the unit circle?